Speed of a longitudinal wave. In a longitudinal wave, the constituents of medium oscillate forward and backward in the direction of propagation of wave, And as the sound travels in the form of compression and rarefaction of small volume elements of air, the property that determines the extent to which the volume of an element of a medium changes when the pressure on it changes is called bulk modulus, and mathematically it is minus delta P divided by delta V by V. Now, since the longitudinal wave in a medium travel in the form of compression and rarefaction or changes in density, the inertial property of the medium which would be involved in the process is the density, and having the dimensions ml minus 3, and the dimensions of B by rho will be ml minus 1 t minus 2 divided by ml minus 3, means L square t minus 2. And therefore, the speed of longitudinal waves in a medium will be B by rho under the root, because the speed has the dimensions of Lt minus 1. So the speed of propagation of a longitudinal wave in a fluid therefore depends on bulk modulus and density of the medium. In case of a solid bar, modulus of elasticity means the Young's modulus and the density rho. So the speed will be given by y by rho under the root. In the case of an ideal gas, the relation is PV is equals to N kBT. For an isothermal change, by differentiating it, you will get V equals V delta P plus P delta V will be 0, means the bulk modulus B is equals to P. Therefore, you can say that the speed of a longitudinal wave in an ideal gas is given by P by rho under the root. And this relation was given by Newton and is known as Newton's formula. As 1 mole of any gas occupies 22.4 liters at standard temperature and pressure, therefore density of air at STP will be 1.29 kilogram per meter cube, and by putting the value in the Newton's formula for speed, you will get the speed as 280 meter per second. But you know that the exact value is nearly 331 meter per second. So this value is 15% smaller. And the basic assumption made by Newton that the pressure variations in a medium during propagation of sound are isothermal are not correct. Later on, it was pointed by Laplace that the pressure variations in the propagation of sound wave are so fast that there is a little time for the heat flow to maintain constant temperature. And these variations are adiabatic, not the isothermal. For adiabatic processes, the ideal gas equation satisfies PV raised to power gamma is constant, and on again differentiating it, you will get it as the gamma P, not simply P, where gamma is the ratio of two specific heats, Cp by Cv, and therefore the speed of sound will be given by gamma P by rho under the root. And this modification of Newton's formula is referred as Laplace correction. And you know that for air, the value of gamma is 7 by 5. And if you put this value in the above equation, you will get the speed as 331.3 meter per second, which agrees with the measured speed. Superposition principle of waves. Consider two waves traveling simultaneously along the same stretched string in the opposite direction. And the sequence of pictures shown in the adjacent figure depicts the state of displacement of various elements of the string at different time instant. Each picture depicts the resultant waveform in the string at a given instant of time. As shown here, a sequence of pictures depicting two pulses traveling in opposite directions along a stretched string, and they meet and pass through each other and move on independently by the sequence of time snapshots from A to D. And the total disturbance is the algebraic sum of the displacement due to each pulse. It is observed that the net displacement of any element of a string at a given time is the algebraic sum of the displacements due to the each wave. And this way of addition of individual waveforms to determine the net waveform is called principle of superposition. And in mathematical form, the displacement y of an element of the string when the waves overlap is given by y, a function of xt. It will be equals to y1, again the function of xt plus y2, and so on. The principle implies that the overlapping waves do not in any way alter the travel of each other. If we have two or more waves moving in the medium, the resultant waveform is the sum of wave functions of individual waves. That is, if the wave functions of the moving waves are y1 is equals to f1 x minus vt, y2 is equals to f2 x minus vt, and so on, then y will be the summation I is equals to 1 to n fi x minus vt. Let a wave traveling along a straight string is given by y1 equals to a sine kx minus omega t, and another wave shifted from the first wave by phase phi will be given by y2 equals to a sine kx minus omega t plus phi. Both the waves have the same angular frequency, same angular wave number, and the same amplitude. They travel in opposite direction of x-axis with same speed. Their phases at a given distance and time differ by a constant angle phi. These waves are said to be out of phase by phi or have a phase difference of phi. Now applying the superposition principle, the resultant wave will be the algebraic sum of these two equations, and by using the trigonometry relation sin A plus sin B, and by applying this relation in equation 4, you will get the function y will be equals to 2a cos phi by 2 sine kx minus omega t plus phi by 2. And this equation gives you the resultant wave, which is also a sinusoidal wave traveling in the positive direction of x-axis. Where the amplitude A will be equals to 2a cos phi by 2. If phi is 0, the two waves will be in the same phase, and the equation 6 will reduce to 2a sine kx minus omega t. The amplitude of resultant wave is 2a, which is the largest possible value of a. If phi is equals to pi, the two waves are completely out of phase and the amplitude of the resultant wave reduces to 0. And for all x and t, y will be equals to 0. And both the cases are shown in the diagrams C and D.